we saw how pointwise estimates and boundedness of Riesz potential give a proof of Poincare inequality, more specifically PP Poincare inequality on balls. We, for the sake of completeness, now show how Sobolev inequality can also follow from similar arguments. You need a new bound on the Riesz potential, but otherwise the argument is very similar. The pointwise estimate that is relevant for us in this case is that at almost every x, value of ux is bounded by the Riesz potential of the gradient. The main difference here is that we don't subtract the average of the ball from the left-hand side. And the problem why we have to subtract the average in that case for the finite sets is the problem of constant functions. But if you have a constant function and it happens to be in W1P, in particular it's LP integrable, and the only constant function that can do this is the zero function. So Sobolev functions defined on all of our n voluntarily vanish at infinity. So you can say that the normalization is just zero. It's ux minus 0. So the case of when dealing with all of our n and the case when you're dealing with balls or just arbitrary open subsets is a bit different in this regard. So the case of constant functions poses some difficulty. Now the Riesz potential can also be defined with any factor alpha positive instead of just 1, and because the theorem of boundedness that I'm about to quote from Juha Kinnunen's notes is for arbitrary alpha positive, I decided to also introduce this object, which may be useful with other factors than alpha equal to 1 in other contexts. The boundedness needed for Sobolev inequality, not just Poincare inequality, is theorem 2 here. You have arbitrary alpha positive, p strictly bigger than 1. It's important that it's strictly bigger. And yet alpha is not too big so that alpha p is less than n. So for the case of alpha equal to 1, this would just translate to p strictly less than n, the familiar assumption in the Sobolev inequality that we're about to see. Then there is some constant which only depends on these parameters np and alpha, so that the Riesz potential of any function that is in LP, so if you give me a g in LP Rn, the Riesz potential that I produce out of it with this factor alpha will be in LP star of Rn. And p star here is np over n minus alpha p. Of course, it depends on alpha. In the case of, again, alpha equal to 1, this p star is the p star of the Sobolev inequality. So here, again, this is the heart of the argument that we're about to see, but we're not going to go through proof of this estimate. I refer again to Kinnunen's notes from his website on how such estimate is proved. In the previous video where we proved PP Poincare inequality, we proved such an estimate that LP of a ball is bounded by LP of the ball again. There are key differences here. The P is the same on both sides. Another one is that here P can be any quantity between 1 and infinity. But for the Sobolev embedding case, for this P star case, we have this assumption. It's not for large P. Okay, so the Sobolev-Gagliardo-Nirenberg inequality that has come to be named after successive attempts says that for P between 1 and n, 1 allowed, n not, there exists some constant so that if you have, let me change color for clarity. So if you start with a function in W1P, which a priori says that u is in LP and its gradient, I have also used this notation, the same. Both of these quantities belong to LP, so in this case of Rn. So if you give me a function u in W1P of Rn for this range of P, then the function is actually more integrable. So P star here will be corresponding to alpha equal to 1, and you can verify that this quantity is always at least, not at least, it's strictly bigger than n. And if P is near n, then this actually goes to infinity. So the function becomes very close to being bounded. So the Sobolev inequality, of course, you don't want to memorize such a theorem with precise parameters. After some time working with these stuff, you happen to memorize them, but you shouldn't memorize such parameters. Instead, the message of the theorem is that if you are in W1P, your function is not just in LP, which is the assumption, it's actually in a much more integrable class, in LP star. And of course, the reason is that it's not just an LP function, it's a Sobolev function because it has a gradient which is also in LP. So the boundedness of the gradient in LP sense kind of improves the integrability of the function. So this is Sobolev-Gagliardo-Nirenberg inequality. For the case of P equal to 1 is usually treated differently. It's actually a tricky case. The proof we're about to see is only for P strictly bigger than 1 because the estimate for the Riesz potential we had is only for P strictly bigger than 1. But honestly, here we don't have anything to prove really. So from theorem 1, we have the pointwise estimate that this is bounded by some constant, the Riesz potential I1 of the gradient of u at x at almost every x in Rn. So this function is almost everywhere smaller. Therefore, any integral of this LP star, again all of Rn, is bounded by a constant, the LP star of Riesz potential du LP star over Rn. But then theorem 2 gives a different C, so you get C prime, but it's very common analysis trick that you just keep writing C for C that keeps changing, but we understand that it only depends on parameters and not the particular function u that you have. And this one by the theorem 2 is bounded by LP norm of du, because Riesz potential of any g, so here this is playing the role of g, so this becomes LP norm of Rn. That becomes the end of proof of Sobolev embedding for the case P is strictly bigger than 1. So case of P equal 1 can be done separately, for example, by the usual tricks, but Joachiminen also continues to provide proof using, again, pointwise estimates and calculations similar to above by kind of doing ad hoc lemmas that cover this case. Anyway, so this detour ends here, and we will go back to the discussion of High-Wash Sobolev class on metric measure spaces. I plan to introduce to you Mackenhaupt spaces and other examples of metric measure spaces on which we can ask about the nature of Sobolev High-Wash class. But if you have any questions, please put them in the comments, and thanks for watching this far. Have a great day.